Good job. 1250. All right, let's see what kind of algebra we can look at today. Pull this up on the screen. Make sure we're in the right place. All right, scrolling down. Oh, I didn't get mine turned in. I think I turned it in 0B. Graphing quadratics complete the squares was due Sunday. So that should already be turned in. I have not turned it in. Hasn't given me a 0 yet, though. It usually give me a 0 by now. But this week, November 16th, we are on, oh, look, the last 2 lessons. So we're going to finish this up. And then next week will be the test for right before Thanksgiving. So we'll be done with solving quadratics here by next week. So we're going to look at 3.06, solving equations, and then 3.07, solving them with complex solution, which complex means imaginary. 3.06. Here we go. Oh, why is this folder open? Then close that up. Make it easier. There we go. Here it is, solving quadratic equations lesson. While redesigning her backyard to build a pool, Nadia wants to include a rectangular garden. Nadia is really into these rectangles here. That has an area of 35 square feet in this garden here. So due to the size of her yard and the incoming swimming pool, the length of her garden must be 2 feet longer than its width. How wide and how long will her garden be? So while setting up this problem may seem easy, solving it maybe not. To help Nadia with the dimensions of her garden, you'll need to have knowledge contained in the following pages. So we're going to learn what methods can be used to solve quadratic equations, and how are the solutions, roots, and x-intercepts of a quadratic related. How are the solutions, roots, and x-intercepts of a quadratic related? I'll give you a spoiler alert. Those are all the same thing. It's saying the same thing. Completing the square has been shown a valid method for solving some quadratic equations, but there's not just one way always just to do things. Let's explore some other methods. So solving a quadratic equation by factoring. All right, so ever since learning about square root signs, you've known how to solve second degree equations by taking the square root of both sides. All right, so we'll go ahead and just start some notes with something that simple. Like if we were going to solve this where x squared equaled 9, that's pretty simple, because to solve means we need to know what x equals. Well, the opposite of squaring is square rooting. So square root of x squared is just x. The square root of 9 is 3 or negative 3. There's 2 solutions. 3 squared is 9, negative 3 squared is 9. But that is the solutions. That's the simple, one of the simplest quadratic equations to solve is when x squared just equals a number. And they show us that right there. It equals plus or minus 3. That's another way to write that. You don't have to write as 2 different numbers. You could put a plus or minus in front of it. There's 2 solutions, because 3 times 3 equals 9 and negative 3 times negative 3. But is there another way to solve that? It says, what about if we took the same equation and started out the same, and we subtracted 9 from both sides? Now we've got x squared minus 9 equals 0. And if we remember what we've looked at in this unit, this is a difference of squares. That's a square, which means this factors to x plus 3, x minus 3. If you need to go back to your notes on that, you know, a squared minus b squared equals a plus b, a minus b. That's what it factors to. A squared minus b squared. So this is a squared and that's b squared. So it's x plus 3, x minus 3. Then we just set those equal to 0. X plus 3 equals 0 or x minus 3 equals 0, and solve for x. Subtract 3. Add 3 over here. X equals negative 3. X equals 3. Still, we got the same solutions we got as we got with this one, where we just took the square root of both sides. So there is more than one way to solve quadratics a lot of times. Not always. I'm not going to say always, but a lot of times. So yeah, they said a squared minus b squared is the same as a plus b a minus b. So we set them equal to 0 and solve x plus 3, x minus 3. The factored equation is set equal to 0. The first factor could be a 0 because if you multiply two things together and you get 0, something has to be a 0. Or the first factor, see that the first factor could equal 0. Maybe the second factor equals 0. Maybe x minus 3 is 0. But could be that both of them equal 0. Maybe 0 times 0 equals 0. But anyway, to get 0, something has to be a 0. So that's why we set this x plus 3 equals 0 and x minus 3 equals 0 and solve to get 3 and negative 3. So that works pretty well. If we can factor it like that, if we can get a difference of squares, we can also graph this equation. Let's go to Desmos and say what happens when we take the one that we rearrange, the x squared minus 9. So y equals x squared minus 9. When we graph this, we also see the two solutions, negative 3 and positive 3. It gets that simple, graphing. Where did it cross the x-axis? What are the roots, the x-intercepts, the solutions? Like I said, those are all three the same thing. X-intercepts, solution, the roots of this equation are all right there at x equals negative 3 and 3. So that's three different ways we solved that one problem of x squared equals 9. And really, it's a matter of which one do you prefer, which one are you most comfortable with. Remember this factor tree we looked at a while back? Everything goes through the discriminant to tell you where it goes. There's many branches. Finding the greatest common factor, we've done that. Perfect square trinomials, we've done that. Difference of squares, we just looked at the problem there. Grouping and factoring trinomials and completing the square. These are all things we've done in the last few weeks. These are methods of these methods are the branches of the factoring tree. But to get through the roots, you got to pass through that discriminant. Finding the discriminant identifies what kind of solutions you can have. So let's see. I'm going to have us another example here. X squared minus 4x. So let's write that one down. So if we want to solve this doesn't really work for doing like this. Because we've got an x over here, we're going to end up with a square root of x. That's not going to get us very close to factoring, to solving for x. So let's go more with this method right now. Let's move all the x's to one side. So on the left side, we've got x squared plus 4x. And this is just 0. Now notice we cannot combine these because this is an x squared term and this is just an x. So those are separate. They are not like terms. When we look at this, remember the first step generally we can do in solving anything is a greatest common factor. This we had x squared minus 9. There was no common factor there. But this, both terms have an x. So we can factor an x out. X squared divided by x is x. 4x divided by x is 4. Now we have the factors. These are as simple as the factors get. And just like this, when you have x plus 3, x minus 3, it's equal to 0. Either this is 0 or this is 0. Well, to multiply these together and equal 0, one of these has to be a 0. So either x equals 0 or x plus 4 equals 0, in which case we have to solve this one. So there's the two solutions, x equals 0 or negative 4. We moved everything to one side to where it said equal to 0, and we factored it. And then we set all the factors equal to 0. Now, let's go back to the graphing part of this. We said we could do everything by graphing. We could leave it like it was originally. X squared equals negative 4x. Oh, see, that does something weird. because it's not set equal to 0. It makes 2 lines. But where are those 2 lines at? -4 and 0, which is actually our solutions. If we want to set this up like a y equals, when we moved it over, we had x squared plus 4x. See, that looks more like a parabola now because we've got the equation set up where we don't have an x on both sides. We can say equals y or equals, f of x. But again, we find the solutions, the roots, the x-intercepts to be -4 and 0. So it says, is it possible to solve this without setting it equal to 0? No, because then we would have x equals the square root of -4x. That's like we tried the very first x squared equals 9, where we just took the square root of both sides. Doesn't work with this type of. So we need to write it in standard form by moving everything to the same side. X squared plus 4x equals 0. You can check the discriminant, the a, b, and c. B squared minus 4ac is that discriminant. All we have is an a and a b. C is 0. So 4 squared minus 4 times 1 times 0 means that this is just 4 squared or 16. And 16 says we have 2 rational real number solutions. When you factor it, you factor an x out like we did, delete the x plus 4, set each one equal to 0. You get 0 and -4. And then you can check them by looking on a graph or substituting them back into the equation and making sure that that is actually the solutions. Notice that there were 2 solutions to the equation in the previous example. What part of the original equation, x squared equals, well, it's minus 4x, they forgot the minus, might indicate how many solutions there will be? It's the degree. Since this 2 is the highest degree, that tells you there should be 2 solutions. All right, they got a couple more examples here. This one is just adds a plus 5 now. So now we got x squared minus 4x plus 5. Again, we move everything to the left side to where we got x squared plus 4x minus 5. When we check the discriminant this time, c is not 0. So let's write this one down and check the discriminant to see what kind of solutions it'll have. I'm writing down after it's been moved over. So I wrote this down, x squared plus 4x minus 5. We moved everything to the left side. Let's check that b squared minus 4ac to see if this is even factorable. Because we need to factor this. Get factors like we did on these other ones. So b squared, a, b, c, the coefficients. So 4 squared minus 4 times a is just 1. We don't have a coefficient there. It's just a 1. And c is -5. So 4 squared is 16 minus 4 times 1 is 4. 4 times -5, we got -20. So 16 minus -20. Well, if we subtract the negative, means we add 16 plus 20. 36 is a perfect square. Right? It's the same thing as 6 squared. So this tells us this is factorable. There will be 2 rational real solutions. So factoring, remember, we need 2 numbers that would multiply together to be -5. So all the numbers that multiply together to be -5 is -1 times 5 or +1 times -5. There's nothing else that can multiply together to be 5. It's a prime number. Multiplies together to be -5, but adds together to be 4. -1 plus 5. That's 4. This one is -4, right? +1, add a -5. So this is the product that we need, -1 times 5. So x minus 1, x plus 5. When those add together, -1 plus 5, we'll get the 4. So either x minus 1 equals 0 or x plus 5 equals 0. Plus 1 minus 5. So x equals 1 or -5. That's our 2 solutions. And we knew we'd have 2 very nice solutions because this is a perfect square when we check the discriminant. X equals 1, x equals negative 5. So they check the discriminant. It's 36. It's a perfect square, two real rational solutions. So that means it factors either 1 times negative 5 or negative 1 times 5. But when we add them together, the negative 1 times 5, what adds up to be the middle term. So x minus 1, x plus 5, set them equal to 0. We get 1 and negative 5. And when you graph it, you see negative 5 and 1 is the x-intercepts. They are the x-intercepts. And you can also substitute those solutions back in there. You'll get 1 equals 1 and 25 equals 25. So you know that works. Okay, they're going to step through this one. It's got a little bit bigger numbers. It's got an extra step that you have to account for. So we'll go ahead and look at this. I think we have time to do this.
The first step in the solution process is to write the given equation in standard form. Gather all terms on the left side of this equation to keep the x squared term positive. That leaves 0 on the right side.
All right, that was the first step. Step 2.
The second step is to factor the quadratic expression. Notice that the terms 6x squared, negative 33x, and 45 are all divisible by 3. Factor this GCF from the equation. The GCF of 3 will remain on the outside of the parentheses. To factor the remaining trinomial, multiply the leading coefficient of 2 and the constant term of 15. Find factors of 30 that sum to the middle coefficient of negative 11. You can organize the results in a table. Negative 5 and negative 6 fit both sides of the chart, since negative 5 times negative 6 equals 30, and negative 5 plus negative 6 equals negative 11. Rewrite the middle term of negative 11x as negative 5x and negative 6x. Separate the polynomial into two groups, the first two terms and the last two terms. Factor the GCF from the first group. 2x squared and negative 5x have an x in common. Factor the GCF from the last group. Negative 6x and 15 are both divisible by both 3 and negative 3. So which do you use? If you were to factor 3, the remaining binomials would not be identical. Notice that the binomials 2x minus 5 and negative 2x plus 5 are not identical and, therefore, cannot be considered a GCF that may be factored. Instead of using a GCF of 3 for the last group, try using negative 3. Now there is a common binomial between the two terms which can be factored.
Okay, they're factoring by grouping, in case you didn't recognize that. We've looked at that as well. Step 3.
The third step is to apply the zero product property by setting each of the factors equal to 0 and solving. There are 3 factors being multiplied. They are 3, 2x minus 5, and x minus 3. For these factors to result in a product of 0, 1, 2, or all of them must equal 0. If the first factor of 3 is set equal to 0, the equation 3 equals 0 is created. But 3 can never equal 0. This is a false statement and will not be considered in the final solution. However, the other two binomial factors can be solved to find a solution. When the factor 2x minus 5 is set equal to 0 and solved, the result is x equals 5 halves. When the factor x minus 3 is set equal to 0 and solved, the result is x equals 3. The solutions to 6x squared equals 33x minus 45 are x equals 5 halves and x equals 3. The equation has a degree of 2, and there are 2 solutions.
All right, and finally, step 4, we're going to check to make sure these are right.
The final step is to check the two solutions. Substitute both solutions into the original equation to check for accuracy. First, substitute 5/2 for x. Square both the numerator and the denominator. Simplify by dividing 6 and 4 by 2. Write the integers as fractions with 1 in the denominators. Multiply the numerators and multiply the denominators. Subtract 165/2 from both sides of the equal sign and simplify. The equality indicates that this solution is correct. Now, substitute 3 for x in the original equation. The final result after simplifying is a true statement. So 3 also checks out as a correct solution. Graphing the parabola y equals 6x squared minus 33x plus 45 also serves as a check. The two solutions, 3 and 5/2, or 2.5, are indeed the x-intercepts of the graph.
The history of the quadratic formula. So this is great. I got a video on this. I'll have to put it in the Google Classroom. But a long time ago, math was used in a very structured method. There were not any formulas. There were not any equations. There were no functions. So mathematicians had to use tables for everything. If the city engineer wanted to build a room that had a specific area for storing grain and pottery, he would consult this large table that gave all these dimensions. But the ancient Greeks started observing math through abstract lenses, more where you could use X's and Y's instead of actual having to use a number for everything. They wanted to create rules and formulas that would hold true for all situations, even not the ones that listed on their gigantic math tables. People like Pythagoras and Euclid would lay the groundwork for a masterpiece called the quadratic formula. It would travel through China, Egypt, the Middle East, and India before finally gaining the form that we know it to be today. So the quadratic formula, well, let's just put that in our notes because the more we write that down, the more we remember things. I got it in our notes right here. So write that in your notes as well. I'll put it nice and large here. But the quadratic formula works for every single quadratic equation. Negative b plus or minus the square root of b squared minus 4ac over 2a. And that is the discriminant that we've been using, the b squared minus 4ac. It comes from the quadratic formula. And this will solve every quadratic equation. Even the ones you can't graph because the solutions are imaginary. Especially those. It's great to use the quadratic formula. So let's see. I'm sure they have some sample problems for us to play with on this. Oh, let's see. Oh, let's talk about a little bit the blue part and the red part. Yes, the blue part and the red part. So they've got it kind of broken out as like, I don't remember which they had, but we're going to do our red part as the discriminant. Okay, and then triangle YAC. All right, and negative b over 2a. And what we know about that is negative b over 2a. That is the axis of symmetry. If we have a quadratic equation in this form, x squared plus 4x minus 5, ax squared plus bx plus c, negative b over 2a gives us the axis of symmetry, which is the x coordinate of the vertex, right? And then this is the discriminant. I should know that. B squared minus 4ac is the discriminant. Discriminant. I had to write that with markers. So those parts of it tell us lots of good stuff as well. So using the quadratic formula, we will do this on paper rather than going through their video again. So let me write this one down. So they have this equation. First thing we have to do is we have to put it in standard form, which means it should be set equal to 0. So subtract 9. So we've got x squared minus 4x minus 9 equals 0. Okay, that's standard form, ax squared plus bx. So a equals, well, must be 1 because I don't see a coefficient written there. So it's 1x squared. B is negative 4. C, negative 9. So that's our A, B, and C based off of the coefficients. That's where we get those three numbers, the coefficients of the x squared, x, and the constant term. So let's use our quadratic formula. X equals negative B. Well, B is negative 4, so negative 4 is a positive 4, plus or minus square root of B squared. Again, negative 4 is B, so negative 4 times negative 4 is 16 minus 4 times A is 1, times C, which is negative 9, all over 2 times A, which is 1. Okay, now we have to start simplifying. 4 plus or minus the square root of what? 16 minus 4 times 1 is 4 times negative 9 is negative 36. So 16 minus negative 36 over 2. All right. 16 minus negative 36. That means 16 plus 36. So this is 4 plus or minus the square root of 52 over 2. Can we simplify that? Surely that can be simplified. So let's look at the factors of 52. And specifically, if there's any factors that are a perfect square that we can take the square root of, right? So we don't care about 1 and 52. Let's see, 2 and 26. 26 is not a nice square number. If 4 goes into that, 4 times 13 is 52. And 13 is a prime number. So if this means we could rewrite this, x equals 4 plus or minus the square root of 4 times 13. 4 times 13 is 52. We can take the square root of 4. So this is x equals 4 plus or minus 2 over 2. That's 2 square root of 13 because we can take the square root of 4. It is almost as simple as it gets. We've got a 4, a 2, and a 2. We can cancel out 2 from all of those. If you need to, you can separate that 4 over 2 plus or minus 2 square roots of 13 over 2, because that's really, when you have something like this where you have 2 terms on top and 1 on bottom, you can write them as 2 separate terms. But 4 over 2 is just 2 plus or minus 2 over 2 cancels out. So the final answer is 2 plus or minus the square root of 13. But what does that equal? Well, let's see. Let's get our calculator out. If you want to know, like graphing it, that doesn't help us. We don't know what number to graph. So if we want to know an actual number to graph, see, I don't need all the extra space over there. There we go. Okay, 2 plus the square root of 13. Square root of 13 is 3.6055. So it's about 5.6. So let's make that a squiggly. It's about 5.6. And what's the other solution? The other solution is 2 minus that. 2 minus the square root of 13. What did I get? Negative 1.6 about. So let's close that down. So yeah, one solution is 2 plus the square root of 13. The other solution is 2 minus the square root of 13. And so it's about 5.6 and negative 1.6. Using the quadratic formula. This is nothing that would have ever a factor, because this is not a nice rational number. So the discriminant is the square root of 52, because we calculated the discriminant as part of the quadratic formula. And since that is a positive number, we know there's some real solutions, but they're irrational. That's an irrational number. Let's graph this to see what graphing would show us. Graphing would not show us the exact answer. If it says give the exact answer, that is this. This is the exact answer. That is the true answer. This is an estimate because it's rounded. This is the answer. You want to give this as the answer. 2 plus the square root of 13, 2 minus the square root of 13. But see, x squared minus 4x, and then it was minus 9, minus 9. So there's that negative 1.6. There's that positive 5.6. Again, it's a rounded number, but graphing confirms that, okay, that is the numbers we got. That is actually accurate for the numbers that we have there. So, and if you want to watch the video, go through it. It's got step 1, step 2, step 3 again. That's 3 separate videos. But they get it down and use the quadratic formula as well. Another example, using the quadratic formula, apply and simplify the quadratic formula. Does this one do anything different? Now this one gets some nicer answers. Let me see how much more we got on this lesson. Well, I think we're going to have a lot more of this in the next one. Let's see. Was this the lesson summary down here? Another example. So here's the one we worked on paper: 2 plus or minus the square root of 13. And then this other example up here that they have the videos. No. Which one is it? Oh, that must have been from up above. 1 plus or minus the square root of 5 halves. That's the other one we saw. Since these do not, they've all had a radical in the solution, right? Square root of 13, square root of 5 over 2. This one, apparently, if you do this one, you'll get some nice negative 2/3 and negative 3. So just try solving this by factoring to see what happens. So if you tried to solve that by factoring, 3x squared minus 11x minus 6, when you write it in standard form and you factor it, the sum of the factors that equal 18 are 2 and 9. So you can do it by grouping in that case, because you can rewrite the 11x as a 2x and a 9x and go through the factoring by grouping. 3x plus 2 and 2x plus 3. Set those equal to 0. So if you want another C example on factoring by grouping, go ahead and go through that. Again, I'm not going to take time for that. We're halfway through class here. Let's visit Nadia from the lesson one more time. The area of her garden was 35 square feet. So let's see if we can solve what she was trying to do. She said the length of her garden, flower garden there, had to be longer than the width by 2 feet. And the area is the length times the width, right? So if we have the width multiplied by the width plus 2, because she just said the length is going to be 2 longer. She just don't know what the width is. And she knows it's going to equal 35 square feet. So what this is this is factored form, but this is a quadratic equation, because if we multiply that, we get w squared plus 2w equals 35, right? But this isn't set equal to 0, so it's not quite the factored form. So we got to move the 35 over. So we got w squared plus 2, w squared plus 2w minus 35 equals 0. So we have this negative 35. We need to find the factors of that add up to 2. So 35, of course, is 1 and 35, with one of them negative or the other one negative. But that doesn't help. What else? 35, 5 and negative 7 would be negative 35, or negative 5 and positive 7. And that's about it. 4 doesn't go into that. 8 doesn't go into that. 6, 9. That's it. When you add these together, this is 34. This is negative 34. 5 minus 7, negative 2. Oh, that's close. Negative 5 plus 7, positive 2. So we need this. So this factors to w minus 5, and w plus 7 equals 0. So that means the answer is either width equals, oh, wait a minute. Let's do width minus 5. So we can add 5. That's just a minus, equals 0. Or w plus 7 equals 0. Subtract 7. So w equals 5, or w equals negative 7. Now, there's something important to think about in that case. What were we solving? We was trying to figure out the width of her flower garden with the formula the width times the width plus 2, because the length's going to be 2 longer. And then we came up with 2 solutions. One of them's 5 and one is negative 7. So if I said, what's the solution? And you said, oh, it's 5 and negative 7. No, it's not. You would lose some points because this is put in a real world context. I can tell her, hey, honey, just make your flower garden negative 7 wide. No, that doesn't work. She can't make it negative 7 wide. Make it 5 wide. That she can do. If we check that, 5 and then plus 2, 5 times 7 is 35. So that works. She cannot make it negative dimensions. So in that case, strictly because it's based on a word problem, we would throw this answer out and say the width equals 5. That one, that is a solution for this equation, but in this context, we throw that out because that doesn't make any sense. I can't even find that on my measuring tape. Where is negative 7? I can pull it out all the way to the end and not find negative 7. So think about that. Think about that. I'll put this back up on the screen. So yeah, so we throw out the negative 7. See, that's just not even a valid answer. It doesn't make any sense in this context. W equals 5 is the only answer. So that's things you have to consider sometimes when solving a quadratic equation. If they put it in a word problem, does it make sense? Does your answer make sense? Do we need to throw an answer out? Because that makes no sense whatever. So they go through it. Did you get that it would be 5 or negative 7? Great. Now only one is valid. They both work in the equation, but you can't have a garden with a width of negative 7 feet. So there we go. So a basketball player throws the ball from 6 feet off the ground at an initial velocity of 20 feet per second. How long does it take to hit the ground? Negative 5t squared plus 20t plus 6 is the equation that the ball uses. So this is a good one to use. Let's try this. And then we're going to go to the next lesson here in just a moment. But we need to give us a good example. The height of the ball based on t is negative 5t squared. Because you'll see quadratics used a lot in real world situations such as this. So looking at this, it says use the quadratic formula to solve. That would be straightforward because a equals negative 5, b equals 20, C equals 6. So let's say x equals negative b, so negative 20, plus or minus the square root of 20 squared. 20 times 20 is 400. 4 times a is negative 5. C is 6. So 4 times negative 5 is negative 20 times 6 is negative 120. Subtracting 120 would mean adding. So 2a, 2 times negative 5. So when we simplify this, we get negative 20 plus or minus. We said this was negative 120. So 400 minus negative 120 all over negative 10. Well, here's a nice thing. This negative over negative cancels out, but we still have this one to deal with. So let's not separate them yet. 520. We need to somehow, somewhat simplify that. The square root of 520 is, here, let's pull up our calculator just to verify everything here. 520 is not a perfect square. 520, the square root, see, it's 22.8. That's not a perfect square. But what can we pull out of 520 that might be a perfect square? Let's see. What's the largest number we could pull out? If we had 520, and we know we could pull out a 2, but 2 is not a perfect square. 4 is a perfect square. What does it get when we divide it by 4? 130. Is 130 divided by 4? Oh, that's 32 and a half. That doesn't divide by 4. 130 is 65 times 2. 65 is 5 times 13. We may not be able to pull anything out more than that. If we're not exactly sure, break out 520 to all of its factors and see if you have duplicate factors. And we'll just start with the smallest factors we can pull out of it. This is 2 times 260. And 2 times 130. So there's a pair of 2's. We know that can come out. This is 2 times 65. That's getting hard to see in this. And this is 3 times 15. And this is 3 times 5. So we got a pair of 3's. 2 times 2 times 3 times 3. So does that mean 4 times 9, 36 may be a factor then, because this is 4 and this is 9. If we multiply those together, let's see what 520 divided by 36 is, because if that works nicely, that's a great number to factor out, because it's going to pull a lot out of there. 520 divided by 36. Oh, that didn't work. 4, 9, 36. Okay, what is 520 divided by 9? Yeah, 9 is not a factor of that. Did I do something wrong on that? It's 6. Does 6 go into 520? $520 divided by 6. No, 6 doesn't go in there either. 260, 130. I'm not finding anything. 3 times 15, 3 times 5. 3 times 3 times. Oh, this does it. I pulled a number out wrong there. No, this is not 3 and 15. This is 5 and 13. 5 times 13 is 65. 3 times 15 is 45. That's where our number's wrong. So really the only thing that pulls out of there is a pair of 2's, a 4. Negative 20 plus or minus the square root of 4 times 130 over negative 10. So we can pull this out. x equals negative 20 plus or minus. The square root of 4 is 2, negative 10. So again, to simplify this, we can write this as two different fractions. X equals negative 20 over negative 10 plus or minus, well, since this is a minus, this is a plus or minus, we can just leave it as plus or minus because either way, plus over minus will be minus, and minus over minus will be plus. So 2/10, 2 square roots of 130 over 10. So this simplifies to just 2. X equals 2 plus or minus the square root of 130 over 5. If we did everything right, 2 plus or minus the square root of 130 over 5. I want to see if they got the same thing here. They cheated and made it a decimal. They didn't even try to reduce this. They made it a decimal and said 22 plus 8. They went a totally different direction. Let's see if we get the same answers if we break ours down into a decimal. They cheated. All right, let's convert ours. 2 plus the square root of 130 over 5. Let's see if it's the same number to get. 2 plus parentheses the square root of 130 divided by 5 parentheses. So ours is 4.28. Or 2 minus parentheses the square root of 130 divided by 5.90. I just want to see if we got the same thing they did because we tried to stick with the radical and they got 0.28 and 4. Okay, I got this one the same. I must have done something wrong on this because they did get 4.28. Let's check our math again real quick. Let's do this. Oh, I didn't hit the final equals. I think this was just, we'll see. 2 minus parentheses square root of 130 divided by 5 parentheses. Yeah, it is negative 0.28. It is negative 0.28. We do have the same number. But at this point, they bailed and made that a decimal. I was trying to do it more mathematically accurate. There is the lesson summary. About 35 minutes left of class. Solve a quadratic equation by factoring, by using the quadratic formula. Check your work. They do have some practice problems if you want to do some more practicing with solving quadratics. If 6x squared equals 6, what are the two solutions? There are 10 problems right there. What are the 10 problems? If you said, oh, it's 0 and 1. Yeah, that's it. Okay, next one. So, there's 10 problems there. The next page has 10 problems there. Here is the equation. This is not set equal to 0. You got to move that 8. Here's two answers. Solve each quadratic equation for x. When you submit, I'm just throwing a guess out there. Correct. Great. Gives you 10 problems. So there's 20 practice problems if you need to do those. If you don't have any trouble with it, you can do this. Solve. Obviously, this one does not factor. You need to use the quadratic formula. Here's one that solves. Again, you need to use the quadratic formula if it's got an answer like that. So there's 1, 2, 3, 4 problems that all need to be used with the quadratic formula. But you're going to have to set them equal to 0 first. They're not ready to solve. This one's ready to solve. It's set equal to 0. But these other ones, you got to do a little work first. And here's one where the baseball player hits the ball. Here's the equation to use. And it wants to know how long will it take the baseball to hit the ground. Oh, that's what this problem was. This was one of those, here's the equation. How long does it take for the basketball to hit the ground? Which means we throw out this answer. It doesn't hit the ground in negative 0.28 seconds. It's 4.28 seconds is when the basketball hits the ground. Again, context. Anytime there's a word problem, think, uh-oh, I may have to throw out an answer. Maybe. All right, let's look at, leave 3.07. Solving quadratic equations with complex solutions. This is not going to be much different than we just looked at. In fact, it's only 4 pages, including practice problems. So Bruce Lee, who's a martial artist and movie star, once said, I fear not the man who has practiced 10,000 kicks one time. I fear the man who's practiced one kick 10,000 times. So what do you think he meant by that? I mean, you think championship sports teams practice 10,000 plays one time? Is that how your football team wins? They got 10,000 plays in the playbook, and we're going to practice all of them and see which one we use Saturday? Or do they just take like 8 plays and practice them hundreds of times? This is also true for math. This lesson will offer that practice on reaching one of the more challenging quadratic solutions. Use this lesson to master the skill. Practice, practice, practice. That's how you get good at this. So when solutions are going to be complex, which methods can be used? Imaginary. Sometimes the discriminant will be negative, which means the solutions are imaginary, complex. So here's one completing the square, a review. We're not going to take the time for the reviews here, but you can go through this. It goes through, this was how we complete the square, just to remind you. And we ended up with this, ended up an imaginary solution. Here is the exact same problem using the quadratic formula. Substituting in the B, A, and C and coming to the same solution. So the quadratic formula can always be used if it's an imaginary solution, or if you like completing the square, that's a possibility as well. Remember to solve for the discriminant first to uncover what types of solutions. Right? B squared minus 4AC. So let's look. How many examples we got? We've got a few. This is just the lesson summaries at the bottom of this page. Let's start with this one. We're going to try to solve this. First thing is check the discriminant. B squared minus 4AC. This is already in ABC standard form. B squared is negative 2. Negative 2 squared. Negative 2 squared minus 4 times A is 1. C is 5. So negative 2 squared is 4 minus 4 times 1 times 5. Negative 16 is what our discriminant is. That means that the solutions to this are complex. They're imaginary. They're not real. You're not going to see them if you graph it. It's not going to touch the x-axis. Oh, that's a good thing to look at. Let's just take a look at that first before it's like, well, I'm just going to graph them and find the answers. Not always. X squared minus 2x plus 5. See, it never touches the x-axis. There are no real solutions. So we have to find solutions another way. So let's see. Let's just do the quadratic formula. Negative b, negative 2 plus or minus the square root of negative 16. I've already calculated b squared minus 4ac. It's right here. I don't need to do it again, but it'd be this over 2 times a, 2 times 1. That's a nice thing. I've already got the discriminant calculated. If I want to use the quadratic formula, I know it equals negative 16. So this is negative 2, which is a positive 2, plus or minus negative 16. Well, if you remember our complex lessons about square roots of a negative number, that's 4i. Because it's square root of negative 1 times the square root of 16. Square root of negative 1 equals I. Square root of 16 equals 4. So that equals 4i. when we have the square root of negative 16. All over 2 times 1, 2. So we can break this out to 2 over 2 plus or minus 4i over 2, which simplifies to, that's just 1 plus or minus 4 over 2 is 2. That's the answer. X equals 1 plus the square root of 2i, and x equals 1 minus the square root of 2i. Complex solutions with the quadratic formula. Let's try completing the square to see if we end up with the same thing. Plus 5 equals 0. So remember, with completing the square, we have to move the constant to the other side. So we have x squared minus 2x equals negative 5. I take this middle term, cut it in half, and square it. So negative 2 divided by 2 is negative 1. And when I square negative 1, I add 1, but I have to add it to both sides. Now I know this is a perfect square trinomial because I just completed the square. So this is x minus 1 squared equals negative 4. All right, x minus 1 squared equals negative 4, because when I move that over. Now, if I'm solving this, I take the square root of both sides. Square root of this side is just x minus 1, because those cancel each other out. Square root of this, square root of negative 4 is 2i. Add 1 to both sides. X equals 1 plus, well, it's plus or minus 2i because it's a square root. Plus or minus 2i. So I can get the same answer. Just remember, when I take a square root, it's either positive or negative. Completing the square, quadratic formula, whichever you prefer. They'll both get you there. Let's see what our lesson does. Let's see. Oh, they said, which one do you prefer? So it says you can either complete the square or solve with the quadratic formula. Here's the completing the square. Isolate the term, move the negative 5 over. 1 is that number that completes the square, because we take the negative 2, divide it by 2, and then square it. So we add 1 to both sides. Simplify that. X minus 1 squared equals negative 4. Take the square root of both sides. Square root. X minus 1 equals plus or minus the square root of negative 4, which is 2i. Move the 1 over. It's 1 plus or minus 2i. And here's where they substitute those in. And yes, you can take 1 plus 2i squared minus 2 times 1 minus 2i plus 5. Solve it all down and get 0 equals 0. If you'd rather choose the quadratic formula, they also have that example. Write in standard form. Fact that there's not a greatest common factor. Plug it into the quadratic formula. 1 plus or minus 2i. There it is, 1 plus or minus 2i. Again, same check. Solve x squared plus 3x minus 6. So first they're looking at it by completing the square, and then it says you can take a look by the quadratic formula. X squared plus 3x minus 6. Let's see. I'm going to go down to this video one because they've got both of those for you there. So if you prefer one or the other, look at those examples. But apparently in this one, completing the square was a lot more difficult because the coefficient says the coefficient was different. Let's see. Completing the square. It's all set up with both terms on both sides. This time completing the square, you had to add 9/4 because cutting 3 in half equaled a fraction, 3 halves. And then when you square 3 halves, it becomes 9/4. So that gets a little bit messy. At that point, you might want to say, oh, I think I want to do the quadratic formula. I'm getting into a fraction. I'm having to square and it gets real messy. All right, let's look at their example here, completing the square in quadratic formula. We'll see which one takes longer and figure out which one you would prefer to do. Because if you got a preference of one or the other, they both work. That's the nice thing. Okay, first is completing the square.
Let's start by completing the square. First, isolate the terms containing the x variable. Once the two terms containing x are isolated, what does the new equation look like? It becomes 3x squared plus 12x equals negative 21. Before completing the square, make sure the leading coefficient is 1. What must be done to the binomial to accomplish this? Factor the GCF of 3 from the left side of the equation. The equation becomes 3 times the quantity x squared plus 4x n quantity equals negative 21. To complete the square, 4 must be added to the binomial inside the parentheses. To keep the equation balanced, 12 must be added to the right side of the equation. Now, factor the perfect square trinomial. Combine like terms on the right side of the equation. To solve for the variable, it must be isolated using the reverse order of operations. What is the first step? That's right, divide both sides of the equation by 3. Great job! Next, take the square root of both sides. Be sure to completely simplify the radicals. Finally, the real number part is subtracted from both sides of the equation.
All right, there's your solution. Negative 2 plus or minus I square roots of 3. Since that is a prime number, we can't take a square root of that. Let's compare that to quadratic formula. See how many steps this takes. So yeah, this is just on page 2 of the lesson. So I don't play any videos
The
here
first step
generally,
is
but
to
you don't
write
have
the
to
equation in standard form. But this equation is already in standard form, so you may proceed to the next step. Next, factor the GCF. Is there a GCF in this trinomial? Yes. Each term is divisible by 3. So, 3 times the quantity x squared plus 4x plus 7 equals 0. Now apply and simplify the quadratic formula. A equals 1, B equals 4, C equals 7. Substitute the values of A, B, and C into the formula. Simplify the exponent. 4 squared is 16. Multiply the appropriate integers. The negative of 4 is negative 4. 4 times 1 times 7 equals 28. 2 times 1 equals 2. Combine the like terms inside the radical. 16 minus 28 equals negative 12. Because there is a negative radicand, a negative 1 must be separated to simplify the imaginary number. Square root of negative 12 becomes the square root of negative 1 times the square root of 12. So, x equals the quantity negative 4 plus or minus I square root of 12 all over 2. Continue simplifying the radical. I square root of 12 equals I square root of 4 times square root of 3. So, x equals the quantity negative 4 plus or minus 2I square root of 3 all over 2. To ensure that you are simplifying the fraction completely, separate it into 2 fractions and simplify each one. Be sure that when the fractions are separated, the denominator remains the same on both. X equals negative 4 over 2 plus or minus 2I square root of 3 over 2. So, x equals negative 2 plus or minus I square root of 3.
So either way, you get to the same answer. Now, I want to point out something here, because a lot of times this is where people struggle. Over here on the right side, right? I get to negative 4 plus or minus I squared to 12 over 2. I'm like, okay, I'm not really sure where to go from here. If you show your work, like if we have this on test, and it's one of those show your work problems, and you get to there, I'm going to give you at least 8 out of 10 points, maybe 9 out of 10. If your work is all perfect through here, the fact that you can't simplify it to this, if that's what you're struggling with, is a very, very small piece of the pie. Right? If you can get to right here, -4 plus or minus I squared to 12 over 2, that shows me you know how to use the quadratic formula. If you get the wrong answer down here, that just means you struggle in simplifying a radical, which is okay. We don't do that enough to really get good at it. Hopefully you can, but show your work and show that you can use the quadratic formula correctly and that you can get where you need to get. Here is the lesson summary. Basically, it's just completing the square and the quadratic formula, the steps to do that, because that's the two ways to solve quadratic equations that have imaginary solutions. That is the two ways we can do that. So let me see. They do have one page of practice problems here with 5 problems. It says solve each quadratic equation on your own paper. Select C for you're correct. Here, well, let's do one of these. That one looks interesting. Let's do this one. So we'll write this in our paper. 2x squared equals 16x minus 50. Now remember, we need to set it equal to 0. So we need to move the 16x and the 50.
About selecting anything right now until your triangles are.
So now on the left side, we have 2x squared minus 16x plus 50 equals 0. Okay, so at this point, we have to decide if we're going to do the quadratic formula, which we've got A, B, and C, or do we want to do completing the square, which means if we're going to complete the square, we're going to need to factor out a 2 and simplify this as much as possible. Okay, well, let's complete the square first, and then we'll see how much time we got. So if we factor out a 2, x squared minus 6, oh, it's not 16 anymore. I just factored out a 2. Minus 8x plus 25 equals 0. Okay, I need to move the 25. Or should I move that first? Because I'm not moving 25 right now. I guess it's multiplied by 2. So this is actually moving 50. If I take it out of here, it's 2 times negative 25. I should have just moved it first. It'd been simpler. So if I moved it first, we would have 2 times x squared minus 8x on this side and negative 50 over there. It gets complicated when you factor something out and then try to move it. Right? Got to remember, this is not negative 25 when it's being multiplied by 2. But this is what we have. If we were to skip this step and just move the 50 to start with, we'd have factor out the 2 times x squared minus 8x. Now remember, completing the square, we got to add a number that is half of this squared. Negative 8, cut it in half is negative 4. Negative 4 squared is 16. But to balance the equation, I got to add it to this side. This is where I do have to take that into account. I didn't add 16 to the left side. I added 32 because everything inside the parentheses is being multiplied by 2. It's twice as big as it looks. So if I add 16 there, I've got to add 32 over here. So let me highlight to show that that goes together. That's why we added 32. It's because of this parentheses. So now we know this is x minus 4 squared because we created that. We made this a perfect square trinomial that this is the factors. Negative 50 plus 32 is negative 18. Okay, now we just need to solve this. First thing is divide by 2. X minus 4 squared equals negative 9. Take the square root of both sides. X minus 4 equals the square root of negative 9, which is plus or minus 3i. Right? Because this is the square root of negative 1 times the square root of 9. Square root of 9 is 3. Square root of negative 1 is I. And it's plus or minus because we're taking the square root. Add 4x equals 4 plus or minus 3i. That's the time. Oh, good. We'll do the quadratic formula as well. X equals negative b. Well, where did we start? We started right here. Once we got it in standard form, we started up here, but we need to move it to standard form. So b is negative 16. So negative 16 plus or minus the square root of b squared. Negative 16 squared. That's 4 times a times c. All over 2 times a, which is 2. So x equals 16 plus or minus the square root of what? Well, let's see. Let's calculate that. 16 squared. 16 times 16. Let's get our calculator so we don't mess anything up because we've also got a 50 and a 4 and some big numbers. We've got to make sure we're calculating the right numbers. So 16 squared. Well, negative 16 squared. Either way. Negative squared. Oh, to the second power. It's 256. Okay, so 256. I'm just gonna write it over here. 256 minus 4 times 2 times 50. Okay, so let's calculate it. 4 times 2 times 50 is 400. So we've got 256 minus 400. Negative 144. So this is negative 144 all over 4. Well, that's nice. This factor should just be 12i, right? Because that's negative 1 times 144, square root of both of those. So this is 16 plus or minus 12i over 4. Well, again, if we split these, 16 over 4 equals 4, and we split that plus or minus 12i over 4 is just 3i. Now, look, we got the same answer both ways. 4 plus or minus 3i. One with completing the square, the other using the quadratic formula. So again, it's whichever one you like. Is that the same problem? Oh, no, wait. Previous. Check my work. 4 plus or minus 3i. And depending on which way you worked it, they'll show you how to do it. We did it both ways, but we got the right answer. Our assignment, solve this. And look, it's going to have complex solutions. Solve this. This needs to be set equal to 0. It's got complex solutions. This one's already set equal to 0. This is in standard form. This is not. You got to set it in standard form. Looks like five problems. Okay, before we go, since we're talking about the quadratic formula, and we got 9 minutes, we're good. I'm only going to take a couple of them. I made a video back during the pandemic because, well, let's face it, I was bored during the pandemic, as probably most of you might have been. I was bored, and so I made a video about the quadratic formula based on, I still remember this from college, and I was in college long before you even thought of. Your folks probably weren't even married when I was in college. And I had a professor called Dr. Chen. He was from China. Dr. Chen, he was my math teacher. One of my math courses. I don't even remember which one. I don't remember if it was trigonometry or calculus or what it was. But he talked about the quadratic formula and told me a story that I still remember to this day. And I made a video on it. So we're going to watch this video and then you'll be dismissed. It's 2 minutes and 36 seconds long. It's on my YouTube channel, but my teacher channel. It has over 600 videos on my teacher channel. But let's see. Here it is. So this is past me. This is me 5 years ago. I'd only had leukemia once at this time. I have had it twice now, but at this time I'd only had it once. But here you go. Enjoy a little something about the quadratic formula that my professor told me. And this was my studio that I did during the pandemic. I had my own studio we set up at the house. So
we are going to learn the quadratic formula. Probably the biggest tool that we're going to have in our math tool belt that we've built this year is the quadratic formula, and it's you can solve whatever quadratic equation you got it right here. So in fact, I had a professor back when I went and got my bachelor's degree, a couple of lifetimes ago, whatever that was. I had a professor in the math department, Dr. Chen. I loved Dr. Chen. He was from China and still had a very heavy accent, and so sometimes it was kind of hard to understand him, but he was very entertaining. He's very knowledgeable. Sometimes he had trouble explaining it to us because of how much he knew about it, but he liked the quadratic formula. In fact, he had a story about the quadratic formula that he told us. Let's see, what was that Dr. Chen said? Alexander the Great, he lived thousands of years ago, and he was a great conqueror. And he went and conquered the countries around him. He conquered that country, and then he conquered another country, and then he conquered another country until he had conquered all the countries of the world. Then he went back home. His friends came over to celebrate, and Alexander was like, boo-hoo, boo-hoo. His friends are like, Alexander, why you cry? You conquer all the countries in the world. And Alexander say, boo-hoo, I cry because there are no countries left to conquer. Well, with the quadratic formula, you can cry too, because there will be no equation that you cannot solve. I'm going to need a moment. That was beautiful. That was beautiful. All right. Yes, thank you, Dr. Chen. I still remember that story. That was just, all my college years, you're one of the few professors I can still remember by name and some of the stuff he did in class. And that was an awesome story. I don't know how many times I've told that in all the years, but I love that story, Dr. Chen. Thank you.
there is Dr. Chen's story. Now you can cry too, because with the quadratic formula, there will be no quadratic equation you cannot solve. So that's why Alexander the Great was crying. There was no countries left to conquer. There could be no quadratic equations left to conquer with the quadratic formula. But this is an A-Day Friday, so I will not be here for this class on Friday. I'll be here Wednesday, but I have a doctor's appointment Friday afternoon, so I will miss in the afternoon. I'll be here in the morning, so you can still email me on Friday if you're needing something. But otherwise, go have a great weekend. And think of Dr. Chen if you need the quadratic formula.